everybody. In this video, we're going to talk about Jefferson's method of apportionment. So take 3 deep breaths and let's make this math easy. All right, so in our last video, we talked about Hamilton's method of apportionment. And one of the main uses of apportionment is how we distribute the representatives we have in the House of Representatives between the states in a way that fairly reflects the population of those states. But like I mentioned in the last video, you can also use it to determine how many employees you should have during each shift, how you could fairly split up maybe some candies between a certain number of people. And there's lots of different applications for apportionment. And Jefferson's method of apportionment was used after Hamilton's method because there turned out to be some issues with Hamilton's method of apportionment. And so Thomas Jefferson introduced the Jefferson method of apportionment, and the United States used his method for a couple years before they switched to another method because Jefferson's method also had some issues with it. So the way that Jefferson's method works is very similar to Hamilton's method, but there's one difference. So the first 3 steps are exactly the same, where you're going to find the standard divisor, then you'll find the quotas, then you'll find the lower quotas. But the difference is that instead of using the decimals to assign the extra representatives, you actually change the divisor until the lower quotas add up to the total number of representatives. So as an example, let's use this same example of Denmark and look at how Jefferson's method would be different than Hamilton's method. So since we've already done all of the calculations for this example, I'm just going to go ahead and copy this down from what we did in the last video. So to find the standard divisor, you start off by finding the total population. So when you add up the populations of all of these individual regions, you get a total population of 5,873,420. Then you take that number and you divide by the number of representatives that you're trying to split up. And so we would take that number, divide by 175, and that gives us a standard divisor of 33,562.4. Then we'll take that standard divisor and take each of the individual populations and divide it by that standard divisor. And when we do that, we get 55.6, 39.9, and 17.6, and 25.1, and 36.5. And that means that our lower quotas are going to be 55, 39, 17, 25, and 36. Because again, the standard quotas represent how many representatives each region should get, but you can't have a decimal of a representative. And so our lower quotas, when we add these representatives up, adds up to a total of 172 representatives. But we have 175 representative seats available. And so we need to figure out how we're going to assign those extra 3 seats. And with Hamilton's method, you do it based on the decimals. But with Jefferson's method, what you do instead is you decrease the divisor slightly until your lower quotas add up to the total number of representatives you want to have. So in this example, let's maybe decrease our divisor and make it 32,000. So I'm taking my standard divisor and I'm going to decrease it just a little bit. And then I'm going to divide my populations by that modified divisor. So if I take the capital region of 1,867,948 and divide by 32,000, I end up with a modified quota of 58 when I round the decimal down. There is a decimal part to it, but you can't have a decimal of a representative, so I'm just going to round that decimal down. And then I'll do the same thing for the central region. So 1,341,857 divided by 32,000. And that gives me the number 41. So that would be that modified quota. Then I would do the same thing for the northern region. And I'd say, okay, well, I have 591,740 divided by 32,000. And that would give me a lower quota of 18. Then I would do 843,513 divided by 32,000. And that gives me a lower quota of 26. And then I would do 1,228,362 divided by 32,000. And that would give me a lower quota of 38. Then I'm going to add up those lower quotas to see how many representatives I've distributed. So I would have 58 plus 41 plus 18 plus 26 plus 38. And when I add those up, I have 181 representatives. But that number is too big because I only have 175 of them. And so what that means is I basically modified my divisor too much. So I'm going to erase all of this modified quota stuff. And I'm going to try again with a divisor that's a little bit closer, but still modified from my original divisor. So since 32,000 was too big of an adjustment, let's maybe try 33,000. So if I try that one and I divide all of my populations, I end up with the following lower quotas. And if I add these lower quotas up, I get 56 plus 40 plus 17 plus 25 plus 37, and that gives me a total of 175 representatives. And so that would be the apportionment that is determined with Jefferson's method of apportionment. So the strategy is basically you modify the divisor until your lower quotas add up perfectly to the number of representatives you want to apportion. And you might have to try it a couple times, like you saw in this example. My first modification was too much. And so I had to change my modified divisor so it was a little bit closer to the original divisor in order to get my results. So why don't you guys try this one on your own? In this one, you'll be scheduling 30 staff members depending on the number of customers that come during each shift. So actually this should say customers, not population. So use Jefferson's method to apportion these 30 staff members to each of the shifts, and pause the video and then restart it to see how I would solve this one. All right, so to start this one, you're first going to figure out what the total number of customers is. So we'll add up all of the customer numbers, which gives us a total of 293. And then I'm going to divide those customers up between all of the staff members that we could schedule. So we're going to do 293 divided by 30, and that gives us a standard divisor of 9.7666, etc. And so my standard quota, if I do 20 divided by 9.7666, that would give me 2.04. If I do the midday customer numbers, so 97 divided by 9.7666, that gives me 9.9. And then if I do 42 divided by 9.76666, that gives me 4.3. And then I'll do 134 divided by 9.76666, and that gives me 13.7. So my lower quotas are going to be 2, 9, 4, and 13. And when I add all of those up, 2 plus 9 plus 4 plus 13 equals 28, which means that I still have 2 more staff members to assign. And if I was doing Hamilton's method, I would do it based on the decimals. But because we're doing Jefferson's method, we're going to decrease the standard divisor slightly until our lower quotas add up to 30 exactly. So I'm going to modify this divisor and decrease it to the number 9 and see what that gives me. So when I do 20 divided by 9, that gives me a modified quota of 2. because I got 2.22222, but if you round it down, it just is 2. Then 97 divided by 9 is a modified quota of 10. 42 divided by 9 is 4, or 4 when you round it down at least. And then 134 divided by 9 is 14. And when I add those numbers up, those add up perfectly to 30. And so this would be my final apportionment. And again, you may have to adjust your divisor a couple times until you get them to all add up to the total perfectly. But that's the way that you use Jefferson's method. So if you have any questions, let me know, and I hope you guys have a great day.